All right, welcome back. Today we're taking a look at the labs for Module 4. That includes Labs 7 and Lab 8. Once again, Exercise 11 is straight out of the book, which means that those are screenshots, so feel free to open up the lab manual and take a look at Exercise 11 before even getting into the practice exam. I'm sorry, the practice lab. But all right, so what are we looking at today? We are continuing to talk about the angle that the sun impacts Earth, talking about the amount of insolation, that is the amount of energy that is being transferred into Earth's atmosphere, as well as the amount of energy that basically hits Earth's surface. We talked about the angle of incidence, right? That is the angle of insolation reaching Earth's surface, and we've talked about this in the previous lab using the analemma, where we know that we were looking at the point where the sun is at its highest, or where the direct sunlight is hitting. And so that is again referred to as the declination point, which on this graph shows that right now the declination point, that 90-degree angle where that direct sunlight is hitting, is at the equator. So you can see over here too that the amount of sun energy, or the intensity of that insolation, is at its highest because it is not being spread out over the curvature of Earth. So when we're looking at the angle of incidence, you can see too that where there is a more shallow angle, right, 10 degrees up here at the north, 40 degrees, 75 degrees, 90 degrees being the most direct, the insolation has a much larger land area to cover, right? All of this space over here, which means that there's less intensity hitting this part of the planet. So the amount of insolation is affected by the curvature of the Earth's surface. This also impacts seasons, and as you can see, the higher the angle, there's a greater concentration of energy and greater warming. So even though we know that in certain times of the year where the sun is going to be shining for 24 hours a day above the Arctic Circle, right? If this is still getting 24 hours of daylight, there's a reason that the Arctic Circle still stays incredibly cold. And that is because of this angle of incidence, the lower concentration of energy, meaning that the amount of heat that will get generated in these pole areas is still going to be far less than the amount of heat that we're going to get closer to the equator or within the tropics. And this unequal distribution of solar energy helps to explain the unequal warming at Earth's surface, right? So the tangent ray, again, is the ray that hits the top of the Earth. The vertical ray is the direct ray, that declination point. And so you can see that the amount of energy is weakened depending on how large that angle is. So how does this angle of incidence impact how energy gets distributed on Earth? Well, there's an unequal warming on Earth's surface. Not only is the amount of insolation, or the intensity of the insolation, impacted by the angle that the sun's rays are hitting Earth, but there are also things in the atmosphere, including clouds, particles, and gases, that may weaken the amount of of insolation that is actually getting to Earth's surface in order to create heat. So again, if we're looking at the thickness of the atmosphere, that is this blue ring around Earth, you can see that at the vertical rays, there is less atmosphere between where the sun's rays is hitting Earth's atmosphere and Earth's surface than if you look up here at the tangent ray, where there's a ton more atmosphere that the Earth's rays have to go through. That the sun's rays have to get through in order to hit Earth's surface. So there's a lot more opportunity for the sun's rays to get deflected, further weakening the amount of insolation that's actually hitting Earth's surface. So again, you can see that the unequal warming, played in part by the angle of insolation, as well as the amount of atmosphere that the insolation needs to reach through in order to hit Earth's surface, is going to cause unequal warming of Earth. So again, this information better helps us to understand the seasons and how temperatures change and how we experience the temperature changes. But again, if we pay attention to the northern hemisphere, this is where we are located, and we can look at whether the northern hemisphere is tilted away from the sun versus towards the sun. This is going to provide our summer months, our warm months, because we are angling closer to the subsolar point, the declination point, where we're getting the strongest sun rays, versus when we are faced away. So as the Earth continues to revolve around the sun, the fact that our axis never changes is what allows the Earth's surface, the northern hemisphere and the southern hemisphere, to experience those seasons as the intensity of the insolation changes, as that declination point changes, where it's hitting, where the direct ray is hitting Earth's surface. And so how's this going to assist us with our lab? Well, we are going to be calculating or using the angle of incidence to take a look at what the angle of the noon sun above the horizon on any given day would be. So it's important to note that if you see a negative number, again, it's described down here as well, but a negative number means that the sun is going to be below the horizon at noon, right? So this is, latitudes on Earth's surface. So we have the equator, we have 45° north and 90° north, meaning this is going to be the North Pole, and if it was 90 degrees south, it would be the South Pole. But we can see that there are certain times of the year where the sun will never be above the horizon, meaning that there are certain months where the North Pole will be in complete darkness as the sun does not shine on the North Pole. So if we take a look at the equator, we can see that there are 2 times out of the year where there's going to be a day where the sun is exactly 90 degrees above the equator. And if I jump back up here, we know that this declination point is going to hit the equator twice a year, on the March equinox and the September equinox. So you just have to know that the same declination point is going to happen right here. But how do we know that? Using this graph, we can see too that sure enough in March, that's the 90 degrees above Earth's surface, right? That's the angle. And in September, we have that 90-degree mark. And so these angles show us the angle where the sun is in relation to the Earth's surface, right? So this is really just talking about the solar angle. And you're going to be using this and deciphering these different graphs where you're looking at the specific day in a specific month to see what the highest solar angle is going to be. Not only are we going to be able to determine the solar angle on specific days of the month, but you're also going to be able to calculate the amount of insolation that is coming into Earth's surface. And that is calculated in watts per meter squared. And so you'll see that as another example as you work through the practice labs. So keeping this in mind, this graph does not actually show accurate data. You wouldn't find this somewhere on the planet. This is more or less just the example giving you a better idea of how to read this graph. So again, paying attention to the solar altitude of the noon sun on the 22nd day of each month. That is what each point represents. And you can see how this angle changes depending on what line of latitude we are looking at on the globe. Also note that you'll be looking at graphs that are talking about the amount of insolation that impacts Earth's surface. And that gets measured in watts per meter squared, basically just watts, the amount of energy that is actually impacting or being absorbed by Earth's surface. And that's the basic rundown for exercise 11 for lab 7. So go ahead and watch the next video so you can get a better idea of what to do for lab 8.